You've got a robot and you've got a controller, but how do you make them work together in the best way possible? Well, that's what we're here to talk about. Let's start with the basics and look at the controller or transmitter first. There are inputs, which are basically everything you can move on your controller. The joysticks, switches, potentiometers, and buttons. On pistol grip radios, this includes the trigger and the wheel. Most modern transmitters run a software called EdgeTX, where each physical input is recorded as a value between -100 and +100. Switches and buttons make discrete values, jumping between specific positions, while sticks, potentiometers, triggers, and wheels all provide analog values, smoothly transitioning as they move. After collecting data from the transmitter inputs, a form of programming called mixing is used in EdgeTX to define how those inputs actually become the outputs that get sent to your robot. An introduction to mixing will be covered in this video. The outputs of the transmitter mix are directly passed to the receiver by your radio's wireless connection. On your receiver, the channels of the mix become PWM signals, which are sent out to the rest of the robot to make it move. Let's start with the basics, making a robot drive. The goal of this video is to start with the bare minimum transmitter mix, which lets you control your robot with one joystick, and then expand on that to make your life easier with extra features. Through this process, you'll be introduced to most of the functions of EdgeTX and get an understanding of how to play with it to make your own mixes in the future. For this video, I'll be using the EdgeTX Companion, a desktop software which makes it easier to visualize and simulate the functions of a robot when creating new mixes. I recommend using it, but this software isn't necessary and all of the steps shown in this video can be done on the transmitter by navigating the menus with the buttons. Moving forwards in the tutorial, I'm going to split the video. The top window will show how to perform the actions in the EdgeTX Companion, and the bottom will show how to replicate the actions if you're only using the radio. I'm using the radio simulator built into the Companion for this, but your radio should be similar enough to follow along. The first thing to do is to import the model and radio settings into the EdgeTX Companion software. If this is your first time opening the Companion software, we'll start by setting up a new radio profile. We'll select the Radio Profiles button, add a new radio profile, and then select our radio from the drop-down list of options. Now, we'll plug in our radio and select USB storage. If you have a newer radio and it isn't working, it may have two USB ports, in which case one of them is likely a charging port and the other is for communication, so try them both. When we plug in our radio, we can close the storage pop-up and select the Read Models and Settings from Radio button to import our current radio models into the Companion software. We'll start by creating a new model for a robot by double-clicking on an empty row. A prompt menu is going to appear, which we'll close because we're just going to be making our own custom mix. This will still leave us with a new model that will open by double-clicking. This brings up the settings for the model that are exclusive to our robot. On the first page, we can rename the model, as well as set up the receiver if we haven't done so already. For now, let's move to the Inputs tab. The Inputs tab is used to define each of the hardware features on the radio that we'll be using to control our robot. We'll start by clearing all of the existing inputs to start from scratch. At this point, it's good to know what the joystick inputs are called in EdgeTX. Since these radios were originally designed for use with airplanes and drones, most controllers use something called Mode 2, which maps the throttle and rudder to the left stick and the elevator and aileron to the right stick. These are just names, but it's important to keep track of them. For this tutorial, I'll cover a basic mix that many people use, mapping the driving to the right control stick. To do this, we'll need to add inputs for the elevon and aileron. We'll do this by double-clicking to create a new input, and then name it FB for forwards and backwards, and change the input source to elevon. For now, we won't change anything else in this menu. We'll repeat the process for the aileron, naming it RL for turning right and left, and changing the source to aileron. Now that we have our inputs, we'll move to the Mixes tab. Each row of the Mixes tab will be a signal that is sent out to the receiver in our robot. For now, we're going to assume that channel 1 is the motor on the left side of our robot and channel 2 is the right side. Let's start again by double-clicking to create the first line of our mix. We'll name this Left M for left motor to help us remember as we continue. By default, I1, which means the input one we set up earlier, is the source for the channel, so we can leave this page for now by selecting OK. Let's press the Simulate button at the bottom to review what we've done so far. I'll also open the radio output view by selecting View, then Radio Outputs. Looking at our radio, we can see that we've successfully linked the Y-axis on the right stick to the output of channel 1. It follows our input. On the robot, this means the power of the left motor would follow our Y-axis input. We'll close the simulator and then repeat the process again for channel 2, naming it, and then changing the source to make sure that it is still input 1 again. When we check our simulator, we now see that channels 1 and 2 both follow the input of the Y-axis. This means our robot is now capable of moving forwards and backwards, but we still need to enable turning. To set up turning, we'll add a new line to the mix in each channel. This is done by right-clicking on the existing mix and selecting Add. Now we'll select input 2, RL. Now the output of channel 1 relies on both inputs, adding together their values to get the output it sends to the receiver. Opening the simulator, we can see this in action by moving the stick in a diagonal. Channel 2 remains the same as it was before, but channel 1 now adds the value of the x-axis position to the value of the y-axis position. When we move in positive x, the values add for a higher number, and when we move in negative x, it subtracts. To create our basic mix, we'll add input 2 to channel 2 as well, but with one small tweak. This time, we'll change the source value from positive 100 to negative 100. This inverts the value from input 2, meaning that the right and left wheels will turn in opposite directions when we want the robot to turn. Now, let's review our basic mix in the simulator again. When we move purely forwards and backwards, the values of channels 1 and 2 remain the same. When we move purely left and right, the values move in opposite directions. If we want to turn left, we move the joystick to the left, and the right motor goes forwards and the left motor goes backwards. This will cause the robot to rotate on the spot. When we move the stick to the right, the opposite will happen. Any combination of those two, with forwards and backwards, will cause the robot to move forwards and backwards while turning. To send this mix back to our radio, we'll close the model and then click the Write Models and Settings to Radio button on the left control panel. Then, we'll restart the radio. This is the simplest form of our mix. In the upcoming sections, I'll show you how to make the motors reverse on a switch to make repairs easier, as well as add throttle curves to make your driving smoother. After the first section, you should have a very basic mix working to drive your robot now. If you tested it at this point, you might notice that your robot isn't behaving as it should be. This is probably because a motor is rotating in the wrong direction due to some soldering in the robot. By adding a few more lines in EdgeTX, we can set up a switch which will reverse the direction of the motor in the robot. When making hasty repairs at an event, this can be very useful because it means you don't have to worry about wiring when replacing a motor. First, let's pick some switches to use. It's a good time to find a switch diagram for your radio so that you know which switches are which. We want to find two separate 3-position switches. We'll create a mix where up on one switch is in the normal direction, down is the reverse, and in the middle is no movement. Having an option for no output is useful if your motor seizes up during a match, as it can prevent your speed controllers from burning out. I'll use switches B and C on my radio. B for the left because it's on the left side, and C for the right because it's on the right side. Let's go back to the mix for our model. First, we need to tell our existing mix that we only want it to apply when switches B and C are in their up positions. We'll do this by opening the editing menu and selecting our switch with an up arrow beside it in the switch menu. For channel 1, I'll set both of the switches to switch B, and for channel 2, I'll set both of the switches to switch C. This means that these lines on the mix only output values if that switch condition is true. Otherwise, it only returns a value of 0. If we play with this in the simulator, it becomes obvious what the switch option in the mix does. It means that the line of the mix only applies when the condition is met. If we change the positions of switch B or C in the simulator, our output stops moving entirely, which is what we want. Now, let's set up the motor reverse directions. In each channel, we'll copy and paste the original lines. Edit each of the new lines by inverting their weight and selecting the switch position down. It should look like this when done, with 4 lines in each channel mix. In the simulator, we can see that the outputs both behave normally when both switches are up, but if we put them both down, the direction of the outputs reverse. This does also work for only one motor at a time. You may notice that this doesn't entirely fix your robot though. You should now be able to get the robot to move forwards and backwards correctly, but it's possible that it might be turning in the wrong direction. This happens when the left and right motors are swapped, but there's an easy fix to this too. If you go back to the Inputs tab, inverting the weight of the right and left turning will cause the robot to turn in the opposite direction. At this point, you can close the model and save the models back to your radio. You should now be able to do repairs even faster without worrying about your exact wiring. There's one last thing to fix with our driving mix. If you've tested it, you might have noticed that the turning on the robot is very sensitive. Let's make some custom variables that we can use to adjust our turning and driving speeds. We'll start by going into the Flight Modes tab and scrolling down to the Global Variables section. We'll make 2 global variables, one called FB for forwards and backwards, and one called LR for left and right. We'll set the forward-backward value to 100 because we want a robot to be fast moving forwards and backwards. Since our turning was too sensitive, we'll set that to a lower number. I'll start with 30, and if I feel like it's too fast, I'll turn it down more, and if it's too slow, I'll turn it back up. This does take some experimentation. To apply our variables, we'll move back to the Inputs tab. For each input, we'll set the weight to the global variable we just created. If you do this right, you should see the global variables showing up in each line of your inputs. There's one last step I like to take when setting up the drive for my robots: adding a small dead zone to my inputs. This can help to compensate for some small motor startup differences and some shaking in your hands. Let's move to the Curves tab. We'll right-click to create a new curve, and I'll name it DZ for dead zone. The curves are used to define how each input behaves. The position of the input values are along the x-axis, and the resulting output values are shown on the y-axis. To make our curve, we'll change to a custom curve and select 6 points. Then, we'll drag them roughly into this loose shape. We'll make fine adjustments with the text boxes, making the values around the center of 0 with a jump on each side. The jump helps to overcome startup stall conditions on both motors at the same time. These values can vary depending on your robot, but I like to start with a value between 5 and 10. If you want, you can also play with different types of curves to try things such as exponential values and other functions. We'll save our curve, then move back to the Inputs tab, where we'll apply the curve to both of our inputs. We'll do this by selecting Custom for our curve, and then selecting the name we just made. If we test our changes in the simulator, we'll see exactly what we want. Small changes don't cause the output to move, but if we travel far enough, we'll see a jump which will kickstart the motors. We'll also see that the turning sensitivity has been turned down. If we want to change that, we go back to the Global Variables section and adjust the values. If you save the config to your remote, you may still notice that your robot doesn't quite move in a straight line. You can make small adjustments to bias your inputs using the Trim tabs on your controller, but this should be avoided if possible. Generally, this is probably caused by a hardware issue such as extra friction in your drive, so you should look into those problems first. At this point, we've finished up with how to set up a drive and covered inputs, mixing, global variables, custom curves, and switches. If your robot has a spinning weapon, we'll cover that in the next section while explaining logical switches and special functions. Let's take a look at the weapon setup, building off of our EdgeTX model we made for driving. We'll assume that your robot uses a brushless motor and ESC wired to channel 3 of your receiver. In reality, You can change the wiring to use whatever channel you like, as long as you adjust your mix to match your wiring. First, we'll add the throttle input on the left joystick to our list of inputs. Then, we'll add it as an input in our mix for channel 3. This is the bare minimum for having it function as desired. If we take a look at the simulator, we can see that the motor doesn't move at all when the throttle is all the way down, and matches the motion of the throttle as expected. This works, but let's take a look at adding some safety features. Having a safety switch is a good idea to help prevent accidents, and also allows you to quickly turn the weapon motor off if you need it. First, let's move to the Special Functions tab. The left box declares what condition being met triggers the special function. If possible, find a two-way switch and set the down position of your switch as a trigger. I'll use switch F. We want our special function to override channel 3, so we'll set that in the action box. In the parameter box, we'll set our value to -100, which is the no throttle condition for a brushless motor. Also double check that the enable box at the end is checked, which lets our override work. Checking in the simulator again, we'll see that the throttle still works normally when switch F is in the up position. When we flip the switch though, we'll see that the value jumps back down to -100, which would stop the motor. This covers most safety cases, but let's add just a few more features to fully flesh out the safety switch functions. Right now, our switch serves as an override, but what would happen if you accidentally flip the switch while your throttle position was not at 0? If we test, we see that the motor would immediately jump up to that value, which could be very dangerous. Let's steal a safety feature from drones and make it so that the motor won't start when you first flip the switch unless you lower the throttle first. To do this, we'll go to the Logical Switches tab in EdgeTX. These functions serve as a very primitive form of logic-based coding. First, we want to detect when our throttle is down, which meets our arming condition. We'll do this by selecting an A is less than X function. For our first value, we'll select channel 3, the weapon output value. Since the absolute minimum value of this channel is -100, we'll set our second variable to -99. The logical switch will now be true every time our throttle is all the way down, which is at the value of -100. The second logical switch will detect when the override switch is flipped to disarm, and will stay true until we lower the throttle. The function sticky will do this. Our V1 value is the trigger condition that will make the sticky function stuck as true until condition V2 becomes true. Since we use switch F down as the disarm condition, we'll use switch F up as our initial trigger. We'll set V2 to our logical function 1, which will make the sticky function false when we lower the throttle. To make our logical switches useful, we just need to move back to the Special Functions tab and create a new function. We'll set it so that when logical function 2 is true, the override for channel 3 is used with a value of -100. Again, double check that the special function is enabled. If we test this function in the simulator, we can see again that our throttle moves normally when the switch is up, but if we switch it to down, our value is overridden. To check that our logical functions work, we'll move the throttle up, then attempt to arm the weapon. Now, we see that our value does not jump up, and the light for logical switch 2 has turned on. When we lower the throttle back to 0, the logical switch turns off, and we are free to use the throttle normally. At this point, you can write the model and settings back to your radio. We've now covered all of the topics to create a solid EdgeTX mix for your robot, and you hopefully learned a good bit along the way. The best way to continue to improve with EdgeTX is to just play with it, so I encourage you to experiment and try making a mix on your own. If you have any questions, leave a comment so that I or somebody else can help you.